In this video, we'll talk about the measurement error in our independent variable x, or the measurement error in our explanatory variable x. Now, typically, measurement error in an explanatory variable x or multiple explanatory variables have been considered of a much more serious problem than or relative to the measurement error in our dependent variable y. So to illustrate this point, you could think about the discussion, or at least base your understanding of the discussion that follows on what you know from our discussion on proxy variables. We can start with considering a case where we only have one explanatory variable for simplicity. So consider this model where y depends on x1 star, and ideally we would want to have information on x1 star, but we only observe x1. So it's similar to this idea that we want information on, let's say, some x1 star that is unobserved, right? But then we are using something else instead of x1 star, which is what we observe. And there is this inherent difference between x1 and x1 star. And that difference is E1, right? So if we think about the relationship between x1 and x1 star in this way, where they're not perfectly related, but there's some sort of a measurement error or a gap, which is an additive gap. It's not a multiplicative gap because this is added to x1 star. We can think about what implications it has. And typically we almost always assume that u, which is appearing here, is uncorrelated with x1 star and with E1, which means it is uncorrelated with x1 star and x1. So there is an assumption that we do make when thinking about these variables x1 star and x1, which is to say that the expected value of y given x1 star and x1 equals the expected value of y given x1 star. So in other words, it is x1 star that affects y directly, and the measure x1 would be irrelevant if we could observe x1 star. So the channel through which y is affected is through x1 star. Okay, so maybe we're observing x1 that affects x1 star, and therefore there's an effect on y. Okay, now since we know from the previous slide what x1 star is, so if we just kind of rearrange this equation, we get x1 star equals x1 minus E1, and we substitute in the value, this right here, into our regression. So in place of x1 star, we're going to substitute in. So what do we get? We basically can say y equaled beta naught plus beta 1 x1 star plus u, and now we can substitute this in and say this is x1 minus E1 plus u, right? So if you rearrange these terms, this is going to become beta naught plus beta 1 x1 plus this composite error that you're left with, which is u minus beta 1 times E1. Now, we've already said that u is uncorrelated with x1. So u and x1 are uncorrelated, and we also said, that E1 and x1 are uncorrelated. So basically we can kind of estimate this equation without the loss of generality. Okay, so we can assume that the same assumptions hold, and we can move on with our estimation. So there's this assumption known as the classical errors in variables assumption, which is stated as the following. So we're basically saying that the covariance between our x1 star and e1, right? So here we are saying that the covariance between the measurement error, e1, and the true explanatory variable x1 star is equal to 0. Okay, and this assumption applies different things, implies different things. So one implication is that the covariance between x1 and e1 depends on the variance of e1. So basically the covariance between the observed x and the measurement error actually depends on the variance of the this measurement error. Okay, and if you look at what is the variance of your observed x1, then that is going to be dependent on the variance of x1 star and the variance of e1. So then the variance is going to be given by this guy right here. Okay, and this is really stemming from the fact, if you want to think about where this is coming from, you basically can write covariance in terms of expected value. So you can say, well, if we're thinking about the covariance between x1 and e1, we can write this as the covariance between x1 star plus e1, right, times, not times, but this is the expected value minus the expected value. So this is what is x1, right? So that's why we are just writing it out this way. And then the expected value of, again, x1 star plus e1, and again this is x1, times the expected value of e1, right? So if you work on this, you're going to get this is equal to the expected value of x1 star e1 plus e1 square minus the expected value of e1 square. Okay, and this is basically going to be equal to the expected variance of e1. Okay, so this is something to keep in mind. Maybe we don't want to get into the weeds of it, but basically the key question here is, what is the covariance between x1 and the error term? So if the error term, this composite error term, were to go up, what would happen to the covariance? Okay, so there are ways to calculate that, and here the covariance between x1 and this composite error is actually negative. Okay, so this is something to remember, and you can see why that happens here. Okay, and then doing some other math here on probability limits, that is, something that you don't want to go into too much detail on right now, because you want to understand what is going on with the measurement error. The bottom line here is that the OLS estimator becomes inconsistent under this classical errors in variables assumption, okay, that we were describing here. So in probability limit, you can write out what beta 1 hat is, and this is going to be a function of beta 1, right? And it's going to be a function of the variance of x1 star and the variance of e1, okay? But it gets reduced to this, okay? So basically this is saying that in probability limit, the estimator, beta 1 hat, equals beta 1 times the ratio of the variance of your true explanatory variable divided by the variance of your observed explanatory variable. And remember that this term can be written as the following. So that term can be written as this term is basically just this, right? This is just sigma square x1 star divided by sigma square x1. So this guy right here is equal to this, and this is less than 1 unless there is no measurement error, okay? So typically there's always measurement error, but we know that this is less than 1, okay? And since this is less than 1, we can say that in probability limit, beta 1 hat, an absolute value is going to be less than beta 1, which is to say that there is some kind of an attenuation bias that exists in the beta 1 hat that we are computing when we are using or when we are encountering measurement error. There's attenuation bias in beta 1 hat when there's measurement error in the explanatory variable. Right? So whatever you're calculating, this is going to be underestimating the true effect. That's what that means. Okay? Okay, so we won't get into the weeds of this, but you know, even if you added more explanatory variables that are not measured with error, you know, you can think about these relationships in more detailed ways, but basically the same conclusions would hold. Now, remember that we can't easily determine the direction of bias in the OLS estimators for these other parameters, beta 2 and beta 3. The attenuation bias calculation has in recent years, and you know, over decades, has influenced a lot of empirical work in economics, but one should understand that it depends critically on this assumption that we were making before, which is to say that the covariance between x1 star and e1 is equal to 0. Okay, so that kind of wraps up this discussion on, you know, what you might get if there's measurement error problems. And typically these happen when you're using survey data, right? If you're wanting, you know, let's say actual savings of a family, or you're wanting actual income of a family, unless you're using like, you know, tax records, which will give you accurate information. If you just rely on surveys, typically, you know, surveys would have this problem of measurement error. And these leads to, this problem leads to attenuation bias in your estimators. And that's really the big lesson from this, this entire video.